All right, welcome everybody to another stream. It's been a while, but I'm back and excited to be here with all of you for another day of streaming some Rust. So, um, the plan for today is going to be an interesting one, I hope. It is going to be an exploration of trait objects in Rust, of dynamic dispatch, and I guess by contrast also of static dispatch as well. So we're going to understand what these concepts are, when you use one versus the other, why do we have to care about this in Rust, what's actually happening underneath the hood, and so hopefully we'll also get a chance to look at go into a debugger and take a look at what's actually happening at the assembly level as well. And hopefully get a better understanding of how Rust handles method calls or function calls in general, because that's something that you actually have control over in Rust, and in many languages you don't have that control. Oh, and it looks like, yes, the stream is improperly titled for those that are watching this live. Sorry about that. I forgot to change the name of the stream. That's a bit embarrassing, but if you're watching this on YouTube, then hopefully I have correctly titled the stream on YouTube. So hello, future. This video is hopefully correctly titled. But yes, we are focusing on dynamic dispatch and trait objects as well, and not on implementing a custom vec type, which I did last time. All right, so let's switch on over to the screen to my code then here. And we're starting with just an empty project here. I just ran cargo new and it's got hello world in it and stuff like that. And in fact, we're gonna real quick change this over to be lib instead. So it's not gonna be a binary, it's gonna be a library instead. I was thinking about good examples for talking about dynamic dispatch, and it's kind of tough to just come up with an example that's relevant for dynamic dispatch and is interesting on its own. But I've been messing around with some other code that has to do with spell checking for another project that I'm working on, and I thought that we could use a spell checker API as kind of a motivation for what we're working on today. And so basically what I want to do is have a function, which, oh, looks like we're in a good state now. Okay. Yes, so let's get started. What are we doing today? We're going to do a spell checker. And really what I want out of this is to have a library that's something like public function that is spell check here. And it takes in, an input, let's say. And it will be of type ampersand stir string slice. And it's going to return back a vector of, let's just do this. It's going to return back a string. And so this whole thing will basically will spell check the input string and return a new string where things have been auto corrected, let's say. And as a second argument here to input, I want to take another thing, which is the spell checker, like this. What type is spell checker going to be? Well, the first thing that we're going to try out is the generic Rust way of just saying some generic type, let's call it C for checker here. And at the beginning of the function, we say we have some generic type C here, right? So now what does this function say? It says it has two arguments, an input of a string slice, and the second argument is a spell checker of some type C. And what do we know about type C? We know absolutely nothing. So we can't really do anything with C because we know nothing about it. It can be any type, literally any type. We're just happening to call it type C here. That's not super useful here. the code that we probably want that I eventually want to be able to write is basically something like, for changes in spell checker dot check or something like that, where we pass in the input. So the spell checker will have a method on it called check, and we're going to pass an input string into it, and it's going to return a collection of changes, of change sets on that input. And then for each, not change, for change, and for each change inside of, for each change that the spell checker returns to us, then we'll do something like, update text, where we pass in the result, which is just going to be a copy of our input here, and we'll pass the mutable handle to our result type, and the change that we want to apply, let's call this, instead of update, like apply change or something like that. And that, for each change that our spell checker returns to us, we apply the change, and then at the end we return our result here. So naturally, two things. First, we have to have an apply change function here. And we can write some docs for it, like takes a change and updates the string with that change. Just like this. So it's going to take a change. And we don't have this type yet, but we'll have some type representing a change that the spell checker returns to us. And it's going to take in a string, a mutable reference to a string that it can update. And this stream is not really about implementing a spell checker. I don't know if this is a good idea for how you would implement a spell checker or not. I can think of several issues with this particular design, but that's not the point. So in here, we're going to just say like to do implement. And for reasons that will become apparent soon, I'm not using the to-do macro that panics at runtime. I really want the apply change thing to do absolutely nothing. So we're just going to ignore these changes. So what is change then? Well, change is just an enum that represents changes that a spell checker might return to you. So for instance, a spell checker might want you to delete certain text. And here we'll have a standard ops range of usize. So the range of text that it wants you to delete from index A to index B, delete that text. Or maybe it wants you to like replace some text. So again, a range from A to B, where it wants you to replace it with some updated string or something like that. So this is our spell checker. It can return changes here, and so hopefully this makes sense, right? We take in an input string, we get an owned copy of it basically here with two owned. So now result here is a string. We're going to call the check method on our spell checker, and that's erroring for maybe obvious reasons, but for reasons we'll talk about in just a second. We get back a whole collection of changes, and for every change that we get, we apply that change to the result string, and at the end we return that result to the user. So this is how we're modeling our spell checker, and this is this is world-class code here. But of course, we have an error here from the compiler saying like, I don't know what check is for type C. Like, I know nothing about type C, and I sure as heck don't know if it has a check method on it. What is this check method, right? And that makes sense. Again, we know nothing about spell checker of type C. We know nothing about type C. It could be usize. Usize doesn't have a check method on it. It could be string. String doesn't have a check method on it. Nothing has a check method on it as far as we're concerned. And in Rust, we have to, we have to give more information than that. We don't have kind of dynamic typing here where it'll figure it out at runtime and give us an error message if there is no check method, and do the right thing if there is. We have to convince the compiler ahead of time. So how do we do things like that? Well, we use traits in this case. So we can say that we're going to have a trait called spell checker. And I'm always confused whether spell checker should be spelled with a capital C or not. I'll go with lowercase c for now. So we have a trait called spell checker, and the trait has one method on it called check. And what check does is it takes ampersand self, so it's a method, it's not a function, and it takes some input string here, and then returns back a vector of changes. All right. So this is our spell checker trait. We now can say that types can implement the spell checker trait if they implement a check method that has, takes ampersand self and an input string and returns back a vector of changes. We're still getting an error up here because still type C could be anything, but the magic happens when we constrain C to be any type as long as it implements the spell checker trait. Pretty straightforward there. And I think that this here is just saying, yeah, result needs to be marked as mutable. That's fine. And now everything is compiling, except, it's complaining that none of this stuff is marked as public, but that's fine. Let's just mark it all as public. And actually, this doesn't need to be public. Oh, yes, it does. Any questions about this so far? Basically, what we've done here is we've modeled a spell check function that can take an input string and any type C as long as it implements the spell checker trait. And it allows us to kind of plug in any spell checker that we want. This is a public function. Anybody can provide us any spell checker that we want, that they want, as long as that type implements the spell checker trait. Looks good, sounds good. If you don't quite understand this, then the rest of this stream might be a little bit too advanced for you, because this is kind of the basis that we're going for. Feel free to stick around and ask questions, but this is kind of the assumed knowledge that you have of Rust so far to get the most out of this stream. All right. So what is happening here? Well, what we're doing is we have a generic function here where we can plug in any type C into our spell check function as long as it implements the spell checker trait here. And so we can go ahead and let's implement a few for illustration purposes here. Let's impl spell checker for let's call it no op spell checker. Check here, and we're going to have some struct called no op spell checker here. And what the no op spell checker will do is just return back an empty vector. So it essentially always finds that there are no changes to make here. All right, no op doesn't do anything, just returns an empty vector of changes. And if we want to have a little bit of fun here, we can do, for instance, what was I thinking about earlier of doing? I think it was like a capital letter spell checker. And this one, what it's going to do is check for words that are completely composed of capital letters. And propose to delete them, basically. It doesn't like capital letters, it wants you to get rid of them. So we can say here, what's the best way to do this? Input dot match indices, and we'll just look for one single space as words. It's not quite right. You probably would want to use a regular expression library or something here to help make this more robust, but that's fine. We can just assume that all words are separated by a single space for now. This will return back an index, index and word, not world. And we can say if the word dot chars, or I think there's an is uppercase. No, I think you have to do this. Chars dot all here is uppercase. So if if all the chars are uppercase, then we're going to, and instead of using map here, I'm going to use filter map instead, which allows us to map and filter at the same exact time, which can be handy here because we can say if it is uppercase, then return back the change of delete, where the range is index and index plus the word's length. And otherwise we didn't find a capital letter word, and so we return back none. And the last thing that we have to do here is collect this up into a vector. Oh, and it looks like we're missing a... Cool. So just to repeat what this does real quick is match indices basically looks for one empty space, and when it finds that, it when actually this is not exactly correct, because we want, this is not the point of the exercise here. Let us go ahead and just change this name to like anti-space checker. This just deletes all the spaces now. And this just makes no sense anymore. We can just do this instead. So now we're just deleting or saying that we should delete all the spaces and stuff like that. So again, we're not actually implementing a spell checker here. This has nothing to do with what we're doing here, but I wanted to implement several spell checkers so that we can see what happens when we use different ones at the same time. All right. So now we have a spell check function. We have two separate spell checkers, and our spell check function is capable of taking either one of them because it is generic over any type C as long as it implements spell checker. And we can prove that to ourselves by writing ourselves a little test here. So CFG test mod tests, and let's use superstar, and I've forgotten how to type. It works. And we can go ahead and say let text equals hello, is it me you're looking for? And we want to spell check this with the text as our input, and the spell checker will first be the no-op spell checker. Here. And we can go ahead and assert that result equals text. So hopefully this works. And it does. Cool. Cool. So we have spell check here. It's using using the no-op spell checker, and down here we can call spell check here with the anti-space checker here, and that also compiles fine. And we won't check the result here. It's fine either way. But the nice part about this is it's generic, and it takes two different types here, because it knows that they both implement spell checker, which is great. All right. Now, this particular form of generic functions here relies, particularly here on when we call spellchecker.check, it relies on something called static dispatch. And what that means is that for each time that we call spell check with a different spell checker, in the case of our test here, we're calling it with two different spell checkers. So each time the Rust compiler will go ahead and create specialized spell check functions for each one of those spell checkers. This is a process, the technical term for it is monomorphization. Basically, it copy-pastes the implementation and differs them based on the two types that we're calling with. All right. Let's look and see if there are any questions here. If I want to fetch and parse approximately 300 links, what would you recommend right now? Oh, if you want to fetch and parse 300 links, if you want to go ahead and do 300 different HTTP requests at the same time, then you might want to just go ahead and use just an async implementation, something like surf or something like that, which allows for parallelization pretty easily. If you just want to use a standard blocking HTTP implementation, then something like Crossbeam probably is the right way to go, or you might be able to use something like Rayon as well. And there's another question about comparisons between capital S string and ampersand string. Does that work? Yes, it does. So there is a implementation for equality checks between own strings and string slices. I don't copy and paste code from the internet. I monomorphize it. Exactly. Cool. So this is kind of the typical way that you would write something like this with generic Rust. Now, when you're out there in the world, you might see a different you might see some different syntax here. Instead of using this generic parameter here, you might see something like this. And we'll have to give it a different name. Spell check 2 here. And this compiles fine. There's no error messages here or anything like that, but this is a different syntax and has a different semantics than what we saw before, but in effect accomplishes something very similar. And in fact, we can see down here, if we want, we can call spell check 2 down here with our text as input and with no op spell checker here and with anti-space checker as well. And this compiles just fine. So there's nothing wrong with this. This works totally fine. And in a way, accomplishes the same exact thing as our original spell check function. We'll have the same results. The same thing will be possible here. There's just a little bit of a difference when it comes to what's actually happening at runtime. And you'll notice here that we have ampersands here. So we're taking references to these things instead of just taking them by value. This is a trait object here. And it is using dynamic dispatch instead of static dispatch, which we'll talk about in just a second what that is. So the first thing that I want to do is like I added this this ampersand and this done. Like what happens if I don't have that? What if happens if I try and do something like this without it? Well, it works. The code compiles, but it's a warning, and I think most likely, and I have a pull request open this on the Rust compiler. This will most likely end up being an error in the next edition of Rust. And the reason for that is because having dyn here makes it very, very clear that we are using a trait object. So the point is to be explicit in saying that this is a trait object here. It's using dynamic dispatch. Spell checker here is a trait. It's not a struct. It's not a concrete type here. This makes that very apparent. You don't have to know that spell checker is a trait. Once you see dyn right here, then you can be sure. You don't have to look at the implementation of spell checker at all. So that's all well and fine. The dyn is necessary just because Rust wants you to be explicit when you're using a trait object here. What happens if we go ahead and remove the ampersand here? In fact, okay, cool. It gives you the error that I was hoping it would give you. It's saying that the size for values of type dyn spell checker plus static cannot be known at compilation time. And this is very important to remember in Rust. You'll often see these types of error messages here about not knowing the size of something at compilation time. What is that all about? The important part for this is that Rust compiles your code, and when it compiles your code, it has to lay out the code in memory. And in order to be able to do that for something like passing arguments into a function, it has to know how much space that argument will take up on the stack. That's an important thing to know when you're creating a stack frame. How much space does your argument actually take up on the stack? Now, if you don't know what the stack is exactly and stuff like that, I encourage you to look into that. It's basically the space that a method or a function call takes up in memory when you're when it's being run, and arguments need to be allocated onto the stack. Some other languages like Java, for instance, which was mentioned in the chat, get around this by basically almost everything except for primitive types in Java are heap allocated. That's not how Rust works. Almost everything in Rust is stack allocated unless you explicitly heap allocate. And when we're passing a trait, we can't pass a trait. A trait is not a thing. A trait is just a contract saying, hey, this is a type that happens to implement this check method here. When we're actually running, we have to pass a concrete type that implements that trait. That can be anything. So it just so happens that our two types here, no-op spell checker and anti-space checker, take up no space. They're zero size types. They don't have anything associated with them, no data associated with them. They have no fields, basically. But we can imagine, adding to our no-op checker some fields here, like I don't know, no-op spell checker doesn't really need any fields, so we'll leave that as 0 there. But down here, anti-space checker, maybe it wants to keep track of like number of spaces here. And we'll do that as a usize here. And we'll change our implementation at some point to keep track of the number of spaces that it encounters for analytics purposes or something. I don't know, I'm just making something up here, right? Now, no-op spell checker takes up no space. It's a zero size type. It basically at runtime it effectively doesn't exist anymore because it has no fields. And anti-space checker takes up how many bytes? 4 bytes. Takes up the size of what a usize is in memory. So these two things have different sizes. So when Rust comes here and says, okay, how much space on the stack do I need to allocate for this spell checker parameter here, it looks and says, okay, when no-op spell checker is being called here, I would allocate 0 bytes because it doesn't exist. It's a zero size type. And when I want to pass in anti-space checker here, I need to allocate 4 bytes here, or 8 bytes actually, because I'm on a 60-bit machine. And that doesn't fly. You can't have a function here that sometimes takes 0 bytes for one parameter, and sometimes it takes 8 bytes. It always needs to take the same size thing, and that's exactly the difference with spell check up here. Spell checker up here really, as we said, it monomorphizes. It copy pastes different functions depending on whatever type we pass in for C here. Essentially, in a way, in this case, to be able to allocate different space on the stack for when we pass in no-op spell checker, it won't allocate any, and when we pass in a anti-space checker, it will allocate 8 bytes for that parameter. So that's how our generic parameter handles this problem. For the trait object, the way that it gets around this is we always have to pass our trait object behind a pointer of some type. We have to pass it indirectly. In this case, we're passing it a reference, but we could also, instead of passing it as a reference, we could pass it as a box. And you can see I got rid of the reference here, but we're still behind a pointer. It's now heap allocated instead of whatever a reference would be. But we have introduced some indirection here so that the type that implements spell checker is living somewhere else, and all we're doing is passing a pointer to it. And a pointer always has the same size. It always is the size of, on my machine, 64-bit machine, it's 64 bits big, it's 8 bytes big, right? On a 32-bit machine, it would be 32 bits big. All right. So this indirection allows us to say, I don't care what spell checker you pass. It could be different every single time, but you're always going to pass it behind a pointer. All right. I've talked a lot. Let's answer some questions. So there's a good question here. What's the difference between using box and ampersand when using the done keyword? So box here is always a heap allocated pointer, essentially. Box owns the thing that it refers to, and that thing necessarily lives on the heap. And when this spell checker gets dropped, which will happen at line 15, the contents of the box will also be dropped. So our spell checker will go away at the end of this function. We know that for sure. It's not borrowed, it's owned here. It just happens to live on the heap. Whereas when we have a reference here, we're borrowing it. So we don't really know where our spell checker actually lives. It could be living in the heap. It could be living in some other method stack frame. Could be somewhere in memory. We don't know. And in fact, it could even be kind of embedded in our binary. We don't really know. We're borrowing it though. And so essentially, the difference between ampersand done and box done is just the difference between ampersand whatever and box whatever. Ampersand references are borrows, and box T is a owned pointer to something. Hopefully that makes a little bit of sense. All right. There's a question about vtables, which we're going to get to in just a second. What's the trade-off here? So the trade-off in this particular case, and we'll talk a little bit more about trade-offs as we get deeper into this, is that spell check here, as we said, will be monomorphized, and so every time we use it with a different type, it will be copy-pasted. What does that mean? That means there's going to be potentially many copies of this spell check function, and that can mean larger binary sizes, because every time you use spell check 1 with let's call it spell check 1 so I can more easily refer to it. Every time you use the spell check 1 with a different type, it gets copy pasted, and that means more code inside of your binary. Spell check 2, there's only one function called spell check 2 that exists in your binary. It's this one right here. It's not being copy pasted for every different type. There's only one spell check 2 function, and that means smaller binary sizes. But you pay in terms of runtime cost for reasons that we'll talk about in just a second. With static dispatch, which is what this function is here, you're just making a straight function call, as in at the assembly level, it's using the call instruction and going straight to wherever this check function is actually implemented, and that's pretty cheap. The call to check here has to go through some indirection. First, it has to go chase this spell checker and find where it's living, and there what it will counter is I guess now is a good time to mention it, as chat did, a vtable. And a vtable is basically a data structure in memory that points to where the implementation of that specific type's methods live in memory. And again, that's going to be a pointer, so it's going to be somewhere else. So it's basically chasing two pointers to go ahead and call that function instead of making the direct function call instead. And that will have performance impacts. Another performance impact on top of that is that Rust can very easily look through this and do a whole bunch of optimizations and see, for instance, if it looks at the check method here and see, oh, you know, that check method's pretty small. I'm going to go ahead and inline the code. I'm going to like take the code from where it is and like paste it in and so I won't call the method. I'll just like paste in the implementation of check in line there because it's small and it will be faster that way. So we don't even actually end up calling the method at all. We just call what the method's implementation is directly. It just gets like the assembly gets plopped in directly there. And that's when things get really fast because you don't have to pay the price of a function call. You don't have to use the call assembly instruction. You just execute the assembly of that method's implementation straight away. You can never do that with dynamic dispatch. Like the compiler just has no way of knowing because this what implementation we actually call is determined at runtime. So there's no way for the compiler to ever really know. It could never inline that implementation because it doesn't know what implementation to inline. Effectively, that's the difference between static dispatch and dynamic dispatch. Static dispatch is determining which function to call at compile time. And dynamic dispatch is determining which function to call, like which implementation of the function to call at runtime. And so all of the interesting optimizations that you can do with static dispatch, which we have in spell check 1, fall away, and you can't do that in spell check 2. So if you use it in really performance sensitive cases, you can end up seeing pretty large performance penalties for it. All right. And yes, as Chad is also mentioning, static dispatch typically will be slower to compile because it has to do that copy pasting and it has to compile to functions and stuff like that. So yeah, there is often the case where you might move to dynamic dispatch because you can pay the performance penalty. It's fine, your code's fast enough even with paying the performance penalty, but you will only have to compile this one function instead of, you know, let's say we have 100 different spell checkers, we'd have to have 100 different versions of spell check 1. Which can get pretty expensive to compile. Is there a difference between spell check 1 and spell check 2 in terms of pure functionality? No, theoretically, like these are, you know, from the answers that we will get back, if we pass in the same spell checker to each one, we'll get the same exact answer for either one. So from a functionality perspective, there is no difference between, in this case, between dynamic dispatch and static dispatch. We will see in just 1 second, I'll talk about how dynamic dispatch can also unlock additional functionality that you cannot get if you need to use static dispatch. So there's another question in chat. Can I do everything I can do with static dispatch that I can with dynamic dispatch? And the answer is no, you can't. And in this particular case, with what we've written right here, the answer is yes. So everything we've written here, there's nothing special about dynamic dispatch other than the performance, both compile times and runtime differences that we talked about, and things like that, binary size, things like that. That's the only difference in this case. But let's take a look at one interesting thing. We rename this to spell check 1. Oh yeah, we added some fields here, which I don't want to do anymore. Cool. So here's an interesting thing that we can do with dynamic dispatch that we cannot do with static dispatch. Let's say we want to run multiple spell checkers over our input text. So we can say let spell checkers equals no op spell checker and an anti-space spell checker. So now we have 2 spell checkers here. Will this, yes, this won't compile. Okay. So this doesn't compile right here. Why is that? Because when we call vec with no spell checker and anti-space checker, we're trying to construct essentially a vector with 2 different types in it. We're trying to construct a vector that has both a no-op spell checker and an anti-space checker, and we can't do that in Rust. And it's essentially for reasons that we talked about before with the function parameter. When we create vectors, we have to allocate enough space in the vector for each item in them, and no-op spell checker and anti-space checker might have different sizes in memory. In this case, they don't. So, you know, go back to thinking where you have different ones, but you know, you need to be able to lay out in memory in your vector. Okay, each space takes up X number of bytes. And the only way we can be sure of that is if every element in the vector is of the same exact type. And no spell checker and anti-spell checker, anti-space checker, are 2 different types. All right, so this doesn't happen. And if we look at the error message, it basically says, hey, I'm building a vector of no-op spell checkers here, and you pass me an anti-space checker. That's not cool. You can't do that. So we can get around that by instead, let's go ahead and box these up real quick. And this, come on. Sorry for the bouncing around here. This also doesn't compile, but it will in just 1 second, so bear with me. For the exact same reason, we're now building a vector of boxed no spell checkers, and now we're passing it a boxed anti-space checker, and that's not cool. So can't do that yet. But if we go ahead and come on, say that this is actually going to be a vector of box done spell checker. Now this does compile, and what we're saying is this vector isn't containing a this vector actually does contain all the same type. It contains in each element a boxed done spell checker, a trait object for this spell checker trait here. And now our spell checkers here is simply just a vector where each element is a owned pointer, a box that points up to this trait object, and the trait object in memory is basically just that V table that we talked about, a place of where it keeps it keeps a table of where its actual implementation for all the methods for the trait that it implements are. And in the case of spell checker, there's only one trait, only one method. So this is fine because every element in the vector is the same size. And we can go ahead, for instance, and loop over our for spell checker and spell checkers. Then we'll call, we'll go ahead and call spell check 2 on the text with the spell checker. And what is it complaining about here? Because we should be able to do this. So I was complaining before that we were passing in a trait, we're trying to pass in a boxed trait object here, but our spell check 2 takes the ampersand done trait object. That's very easy to get around. We just go ahead and dereference the box and then re-reference it. So basically borrow the contents of the box here. And asref should probably work as well, chat. Let's asref. Yeah, it also works. So there's a question in chat again about what is the purpose of the done keyword. Well, again, you don't really need it because this compiles just fine. But we do get a warning and saying, hey, this is a trait object, right? It's not static dispatch. This is dynamic dispatch. And you're not using the done keyword here. And the reason that the done keyword was introduced was basically to make this very explicit. Because let's assume I know nothing about what spell checkers are, and I'm looking at spell check 2 here. I have no way of knowing that spell checker here is actually a trait. That this is actually a trait object here, and that dynamic dispatch will happen here. If I knew nothing about spell checker, if I had never seen this code base before, for instance, I'm not writing it, I have no idea what this is, and I look at it and I go, okay, with spell checker, this could either be a reference to some spell checker type, a struct called spell checker, or it could be a trait object. And before the done keyword was introduced in Rust 2018, around that time it was introduced, there was no way to tell, and you basically had to look, is spell checker a trait? Okay, it is. Okay, this is a trait object. That's how you would know. And the done keyword was introduced to make that very explicit. And now when you look at it, you know right away, this is a trait object. Spell checker is not a struct. There's no way it could be a struct. And in fact, let's try to put no spell checker, no op spell checker here, it'll go, hey, it's like, I expect this to be a trait and you're giving me a struct. It's like, exactly. It's got to be a trait. There's a question, why do we need to re-reference? It's a box ampersand done t. No, it's not. It is a box done t. There's no reference inside of this box. So this works here. What happens if we try and use spell check 1 here? It goes, nope. Like, I'm trying to monomorphize here trying to like create a fresh copy of the spell check 1 function here that where done spell checker implements spell checker, and that's just not the case. Now, I'll leave it to the reader to try and implement spell checker for ampersand done spell checker and see the fun that you get into with that as well. Silly question, which is not a silly question. Why is done pronounced done and not dine? I think a lot of people call it dine. I call it done, as in, not as in done, but done. I don't know. It's just me. Call it whatever you want. D-Y-N. It's also fine. Yeah, din is also, I'm not exactly sure what the kind of like correct way to say it is, or if there even is a like official way to say it. Have to ask the RFC author what their opinion is. Yeah, the old GIF versus GIF or GIF debate. Who knows? So does everybody understand what the like on a high level kind of high level understanding of what the difference between this static dispatch is here, this monomorphized function here with a generic parameter here of type C that implements spell checker versus this dynamic dispatch trait object here with spell check too. Is this making some sense? Now the question might be that's coming up, okay, in this particular case, which one should I pick? Like you said, they're functionally equivalent. Which one should I pick? Well, largely it's going to be the trade-offs that we talked about in this particular case. Like, does binary size matter too much to you? How many different spell checkers will there be? Will you potentially balloon compile times? If this is most of the time, this is going to be what you want in terms of just these, plain function calls here. So most of the time you'll end up seeing this static dispatch type, like this static dispatch kind of pattern being employed for function calls and stuff like that, because most of the time the trade-offs end up being better for static dispatch. Like compile times usually aren't affected too bad by this. It's faster, which is generally what you want to like do by default, is whatever is fastest. Binary sizes, like most of the time, aren't affected too bad by this. It's only when you're using it a lot will you notice compile time and binary size impacts by this. So most of the time you're going to want to pick this. But remember that if you want to support the use cases, for instance, of excuse me, if you want to support the use case of having like kind of these different types of spell checkers in a collection or something like that, then dynamic dispatch comes in pretty handy here. And there's another often use case, for instance, like let's say I have a struct of like my text editor here. My text editor has a ton of fields in it, like it's got the buffer in it, and that's a string, let's say, and it's got the cursor where we are in the thing, cursor, and it's got so on and so forth, a ton of different things. And you also want your text editor to have a spell checker in it, right? Like that's fine. Let's get ahead and have the spell checker here. We have two options here. If we want a pluggable spell checker here, we have two different things that we can do. We can either say our spell checker is going to be, well, we have three options. The first option is pick a concrete spell checker. Spell checker will always be the no-op spell checker, always and forever. And I'll get rid of cursor since it doesn't exist. Now we've hard-coded our spell checker in our text editor to always be the no-op spell checker. We can't switch it out for anything. It's always got to be the no-op spell checker. That's not so nice, right? Then what we can do is say, we'll make this text editor generic on what type of spell checker it is. With two fields, not too bad. Maybe this is fine. But then you always have to think about like a text editor, what generic type do you want to pass it? It makes things bulkier to use and stuff like that. When people are interacting with text editors, they always have to either say, I don't care about what type of spell checker it is, it's some generic type C, I don't care, or they have to plug in which one they actually care about and stuff like that. That's also not so, sometimes not so nice. Maybe it is, maybe it isn't. And the last thing that you can do is say, okay, I'll just make this a box done spell checker. And now notice text editor here is not generic. Text editor is always just a text editor. It's not generic on anything. But our spell checker can be changed out. We could have, for instance, like we could just make this pub here, and people can just say, my text editor.spellchecker is this different type. It's plug and play. You can have any type of spell checker you want. Any type that implements spell checker could live behind this boxed pointer here. And so that's another area where you have to decide, what kind of flexibility do you want? Do you want the ability to plug in a different implementation of this type? And do you want to make your type generic over that? Or would you rather just pay the runtime cost of having it be a trait object and use it instead? And this is how in a lot of languages inheritance ends up working, or and interfaces and stuff like that in Java and C#. Basically in Java and C#, for instance, everything is boxed. Everything lives on the heap except for primitive types. So you don't have special syntax for it, but everything ends up living on, and everything will go through dynamic dispatch. So if this dynamic dispatch sounds funny, most languages, that's just the default. That's where everything goes through dynamic dispatch. There is no static dispatch. It's only really in languages like C, C++, and Rust where this static dispatch plays a role. There's a comment saying this is a confusing type and you might want to have a type alias for it. Yeah, you could do that as well. Type spell checkers is equal to this type, so you don't have to write it. It is a bulky type, that's for sure. So using a box done trait object adds more of a runtime overhead. Yeah, as we talked about before, dynamic dispatch is a little bit of a runtime overhead and can't be optimized as aggressively as static dispatch. Check in on the time. Okay, we're running a little bit low on time because I have a hard-ish stop at in about 45 minutes. So I want to go ahead and start looking at what this looks like at actual runtime. And let's open up a debugger and check it out. So I'm going to clean this up by commenting out some stuff here that we won't need. And let's go up here, and to illustrate the point, I'm going to get rid of most of the implementation of spell check here, and I'm just going to leave the actual call to this .check function. And in fact, let's go ahead and clean it up even more and just say these things don't return anything. So this is kind of a waste, obviously, but this will be good for looking at it in the debugger. All right, we don't need this anymore. Oops. Okay. Let's just use the no-op spell checker. So we're not going to take a look at the anti-space checker anymore. And we're just going to look at calls to spell check 1 and spell check 2. Again, spell check 1 is using static dispatch, and spell check 2 is using dynamic dispatch. All right. There's a question about, does done dispatch add a significant memory overhead? No, it shouldn't be significant. A vtable will be a vtable with one function in it will probably just be the size of one pointer, the pointer to wherever the implementation of that method is, and so so that's 8 bytes or whatever. That's not very big. So memory is not what you need to worry about in terms of overhead for dynamic dispatch. It's really runtime performance and the fact that you have to go through 2 pointer lookups and the compiler can't optimize that away, whereas it can optimize away the static dispatch call. All right. There was a question about using ampersand done spell checker inside of our text editor type that we just talked about instead of boxed done, and that's totally fine. You can also do that, but then you're running into the thing about lifetimes. box is great because it's owned. You don't have to worry about lifetimes and stuff like that. But anytime you borrow something inside of a struct, you will have to worry about the lifetime of that borrow and stuff like that. That's not really specific to dynamic dispatch though. Cool. And then I really hope that GDB plays nice inside of this VS Code terminal here. So let's go ahead and run cargo test again. And you'll see here we ran cargo test. It creates a whole test binary, and this is where the test binary lives, right here. And so what we can do is run GDB on, and I'll run it in TUI mode. It's the terminal UI mode, on target, debug, deps, and this the test binary that we were running. And okay, it seems not too bad, so that's good. So then we can go ahead and say that we want to stop or put a breakpoint at the itWorks function. And we'll go ahead and run. Cool. So let's go ahead and hopefully, I know my face is blocking down below here, and you can't see my mouse right now, for instance. Let me know if I end up blocking something important. I'll try and keep my eye out for that. And I think I can. Yeah, cool. So this is now full-ish screen. Okay, so we're inside of this debugger right now. We've set a breakpoint for the first line of our function. And we're going to take a look at what actually happens when we call spellcheck1 and spellcheck2 and what that looks like in assembly. And don't worry if you're not used to assembly and stuff like that. We're not going to look at it in detail. We're just going to kind of get a rough idea of what's going on here. Okay, so I think the first thing to do would be to go ahead and go here. So now, as you can see over here, we're getting a warning that our test is running very long. That's fine. We are now at the line where spellcheck1 gets called inside of our test here. What we can do is go ahead and run layout ASM, and what that does is switch from the source code here to the assembly that source code represents. So if you can. What you can see here, and in fact, if I scroll up and we just look at here, this is basically the entire itWorks function that we had from before, and we're about to go ahead and call our make a call to spellcheck1 here. All right. So that's cool. So we can go ahead and step here. And now we are inside of spellcheck1 here, and let's go ahead and switch back to spellcheck1. And you can see we're in spellcheck1 here, and all it does is go ahead and call check on the spell checker that we've passed in. All right, so layout ASM here. And don't worry too much about the assembly. Again, all this junk here basically is doing is putting the arguments in the right space and stuff like that, and setting up the stack and things like that. There's nothing too much to worry about here. The important thing is that when right here, this line right here is where we actually call check on our spell checker. And you can see, in fact, that it knows that it's going to be calling check on the no-op spell checker here. So this no-op spell checker as a spell checker calls its check, and it's just one assembly instruction call to go ahead into that function. So we can go ahead and step instruction here with si, and we're going along, we're executing, and then we go ahead and we execute one more instruction and call, and then we're inside of spell checker check here. And spell checker check is not doing too many interesting things here. You know, again, setting up the stack and stuff like that. That's not a bunch of fun. And then it's calling this, you know, vector implementation, because we're basically calling vec new here, and that's it. So, you know, not too fun or anything, but that's basically what's happened here. We've gone into the spell check one function, and we've called using the call assembly instruction directly to the no-op spell checkers check method. Hopefully that makes sense. Pretty straightforward. And a whole bunch of other assembly junk that has to happen for esoteric reasons that don't really matter for today. All right, I'm going to start over again. And this my GDB gets messed up sometimes when I do this. What do I need to? I think I need to call refresh here. Yeah, there we go. All right, let's go ahead and switch back. I've restarted the program. Let's switch back to our source here. So here we are in our source again, and I'm going to call next here, which will go to spell check one, and I'm going to call next again, and it's just going to run spell check one again. We've already seen what happens in spell check one, and now we're at spell check two. Okay, and let's take a look at spell check two here. So layout ASM. So we're about to call spell check two again to go into, or sorry, not again. We're going to go into spell check two here, and nothing very interesting here. We're stepping through, we're setting some arguments up or whatever, and then we're going to call spell check two and go into spell check two. So now we're in spell check two. Let me refresh it again so that it doesn't look all messed up. Now this is spell check two, and spell check two looks very different than spell check one did. Spell check one, remember, like it was like 4, maybe 5 instructions that were like doing these interesting weird move keyword pointer things. Again, setting up some instructions in the stack and stuff like that, or some stuff on the stack, setting up arguments and things like that. But then like around here-ish is when we saw that like the call to, or the assembly instruction for call. And remember, it said like call the no-op check method. So it knew exactly where to go to, but there's no call here. It's all the way, there's all this interesting thing down here, call down here. So like, okay, we're obviously doing more work here than we were doing before, and doing a bunch of stuff. I have no idea what it is. So step. We're getting down here, and then finally, go up again. We finally get down to, sorry, I need to restart. I went one instruction too far, of course. Layout source. Next, and then hello. Okay, then we're in spell check two again. Let's go back to here. We're going to go through just like before, calling all these things. Boom, move, and then finally we get to this call assembly instruction again. But notice that it's not calling just a hard-coded address anymore. It's calling this keyword pointer thing. And if you don't know x86 assembly, basically it has calculated an address, and that's living inside of a register somewhere, and it's going to call the function that lives at this address that it's calculated here. So if you don't care too much about assembly, the point here is we've done a whole bunch of work, and we're more work now than we did before, and we're going ahead and calling a function that we've calculated at runtime, because it wasn't hard-coded in the assembly. We've calculated at runtime, unlike what we had before. All right, before with when we were calling in spell check one, we could just directly call that function. All right. And basically what's gonna happen here, if we go ahead and step in, is like we call the we get the v table. Like that's what was happening before, as we were calculating the address to the implementation that we wanted to call from the v table. We gathered it, we calculated it, and then we go ahead and executed it, and we can go ahead and execute it here. All right, any questions about what's happening here, the difference that we saw in spell check 1 versus spell check 2, and why spell check 1 was shorter and just had that call directly to that hard-coded address, and how spell check 2 was longer and didn't make a call to a hard-coded address, but rather to address that was calculated at runtime. Do we get that, why that is? Again, it's important to point out that the reason for that in our code is because spell check 2, if we go up to spell check 2 here, spell check 2 is calling the check function on a trait object. So it doesn't know until runtime which specific implementation to go to. It needs to calculate that at runtime by using this v table. All right. The last thing that I wanted to show to you that's also interesting. Let's go back here. Oh, and it looks like I totally screwed up the GDB here. That's fine. If we go ahead and set a breakpoint again at it works, I just want to look again at this the static dispatch that we had before. Let's go ahead and run this. And we want to go ahead and step here, and then we want to step again, and we need to refresh this so that you can see it. And again, we're about to call check on our spell checker, and if we look at the assembly code again, here we're back, and again, 1, 2, 3, 4, 5, 6 instructions into the function, we're already at this hard-coded address that we're going to call for check here. But we're going to call a function here, right? We're going to call this no-op spell checker check function. So when we get to this here, we leave this stack frame, we leave this area in memory, and we go somewhere else. And now we're in a totally different area of memory, right? Now there's two interesting things that will happen if we go ahead and change our code. Let's go ahead and add back spell check 1 here with our anti-space checker. And we'll add spell check 2 also with the anti-space checker, but as the trait object. So now we're calling spell check 1 and spell check 2 each time twice with the two different spell checkers that we've created before. Wait, I have to go ahead and compile this, cargo test, and my terminal is all blown away because GDB 2e blew it away. And run here. And we can go ahead and set a breakpoint at it works and run it. So here we are. Again, we've got our text. We've got the 4 function calls that we are going to make. And we can go ahead and check out what that looks like. If we go ahead and go to layout, ASM here, and take a look, you can see up here, this is where we make our call to spell check 1, and then this is where we make our call to spell check 2. And if we scroll on down here, we make our call to spell check, up here was, let me go to the top again. This was the first call to spell check 1, and this was the second call to spell check 1. And then our 2 calls to spell check 2 are here and here. Is there anything that you notice about the addresses that we're actually calling here? If we scroll up to the top, when we call the spell check 1 function, the first time we call it at address 555 whatever 68040, and the second time we call it at 555 whatever 680B0. So we're calling 2 different functions. That proves to you spell check 1 is actually 2 different functions in code. It gets compiled out to 2 separate functions, one that works with the no-op the no-op spell checker, and the other one that works with the anti-space spell checker. But if we scroll to the bottom, spell check 2 here, call is to 555-69860, and this one is also to 69860. So there is only one spell check 2. And that's exactly what we were talking about before of the trade-off between static dispatch monomorphization, where you have to copy paste the code and that can lead to more code, and dynamic dispatch. Dynamic dispatch, there's only one version of spell check 2, and we're calling it right here. But there's 2 versions in our code of spell check 1. And just to prove that to you, let's go ahead and step here. And we're about to call spell check 1. And if we call spell check, we step again and refresh, so this is viewable. Now we're inside of spell check 1, and you can see, just like before, we are going to go ahead and call the no-op spell checker here. The no-op spell checker check. Now I'm going to go ahead and go back up the stack frame again. Now we've returned back from spell check 1, the first call to spell check 1. And I'm going to call then the second call to spell check 1, which again is a separate function. So we step. Sorry. We have to go through all the stuff. I screwed up my GDB real quick. And we're going through the implementation, blah, blah, blah. Drop in place, blah. Okay. Now we've finally reached the point in our entire call stack where we have called spell check 1 again. But look, we're in a different spell check 1 now. We're in the second copy of spell check 1, and here's the call to the anti-space checkers check function. So there we have proven again to ourselves that there is multiple copies of this check function. Does that make sense to everybody? And the last interesting thing that I want to show real quick is if we go in here and add this annotation, inline always. What inline always does is it says, compiler, when you encounter this function call here, I don't want you to compile it down to a function call with the call assembly instruction. I want you to take all the code that's inside of this function, and wherever this check method is being called, just copy paste the implementation right there. So I don't have to pay the overhead of actually calling the method. I want to go ahead and just copy paste the code right in. And this is something that the compiler does often by itself. We're running these tests in debug mode, and so a lot of these optimizations are turned off. And so the inline always is basically like saying, do this optimization no matter what. Even if you, dear compiler, don't think it's a good idea, I want you to do this. There's a question about how smart is Rust C about inlining, or does that happen in LLVM? As far as my understanding right now of the situation is that LLVM does the vast majority of inlining decisions. That there's not a ton in the Rust compiler front end that makes too many decisions about inlining. Except that it can provide hints and stuff like that to LLVM. For instance, inline always there gets eventually just passed to LLVM and say, you have to inline this. I'm telling you. So it does know some about inlining. So let's take a look and see if this makes a difference when we actually run it. So now, again, real quick, just to see, when we call spell checker, the no-op spell checker's check method, it should be inlined. And we can do cargo test. And that will give us a new binary that's been compiled. And we can run gdb2e, and it should be inside of target, debug, deps here. And then we can go ahead and set a breakpoint at it works again. And we'll go ahead and run it. So here we are again. And let's go ahead and step, and we'll step into spell check 1. And now we're going to call the no-op spell checkers implementation of check. We're about to do that. And let's take a look at what this looks like in assembly. And you can tell here already, this is the entire spell check 1 here. There is no call anymore to no-op spell checker's check function. It doesn't exist. We're not calling. We're inside of spell check 1 here. In code, it says call no-op spell checker's check function or check method. But here we don't see that because it's been inlined. And in fact, what is the implementation that we're inlining? It's a call to vecnew, which is right there. So here we can see that we have this implementation where we can inline the call to vecnew directly into the call to spell check 1. But if we go ahead back to source here, my GDB is just loving it here. We're at spell check 1, but if we go and hit next again, now we're going to go into spell check 2. Let's step into spell check 2, which is calling again the no-ops. It's going to call the no-op spell checker's check function or check method, just like spell check 1 originally did. We step into it here, and if we take a look at the assembly here and look at this, then we can see, unfortunately, we're doing all the same work that we did before. We're doing all the same work that we did before, where we're actually going to end up calling right here into the dynamically calculated address of wherever no-op spell checker's check method is. And so inlining was not possible here because, again, we don't know that we want to call the no-op spell checker function until runtime. And so the compiler has to figure that out or the compiler emits code that figures that out at runtime. And so we can't possibly inline that implementation. And this is the reason, oftentimes that dynamic dispatch is slower than static dispatch, because we can't inline. All right. That was a discussion of static versus dynamic dispatch, the differences between the two, a little bit of a discussion about when you would use one versus the other, what the pros and cons of one versus the other are. And what we ended up with is taking a look at the actual assembly code that gets emitted when we use one versus the other to see what impact they have at the assembly level. And we were able to convince ourselves that static dispatch actually ends up producing multiple copies of the function depending on the type that we pass into the function, whereas dynamic dispatch does not. But static dispatch allows for inlining, whereas dynamic dispatch does not. And with that, you know a lot now about dynamic versus static dispatch, and what actually happens at runtime when you use one or the other. And with that, I think we'll go ahead and end it there. If there are any more questions, then I'd be happy to answer that. And please, you can see at the bottom of the screen. No, you can't. You can see if I switch over to here. Oops. At the bottom of the screen here, you can see my Twitter and the YouTube channel where I post this. Please make sure to like, subscribe, all that stuff. Really helps me know if you like this stuff, and let me know on Twitter, for instance, what you want to see more of, if you found this interesting or not, if it was too slow, too fast, too advanced, too beginner. This really helps me because I'm just taking my time out of my day to do this, and so it really helps to know what you think about it. There's a question here about what do you mean by inlining? So we saw before when we added this annotation here, inline always, what the compiler does when it encounters this attribute is it looks at the check method and says, instead of compiling this as an actual function call in assembly, and in assembly a function call is done through the call instruction, I want you to take the implementation inside of this function and just paste it where you would do the function call instead. And so it avoids setting up arguments, switching out the stack pointer and stuff like that, and then going to a different place in code. It just executes the function's body kind of inline directly where you would have otherwise called the function. And that's what inlining does. And that has the effect of making things much faster because there's a whole bunch of overhead that you pay for calling functions at the assembly level that you don't have to pay if the function is inlined. There's a question about what is needed to collaborate with Windows RS. For those that don't know, I'm working on a project at Microsoft called Windows RS, which is a Rust project for interacting with the Windows APIs, the various Windows APIs. And if you want to collaborate, then please open issues, use it, let us know what you think, open up bug issues, and take a look at some of the issues that we have already in the issue tracker, and you can feel free. There's some that are marked, I think, as good for beginners. You can go ahead and implement those as well. All right. Doesn't look like there's any more questions. Feel free to reach out on Twitter, and I appreciate everybody's time. It's been a lot of fun. So I will see everybody around. Bye-bye.